Hi, this will be a video on a problem from the JEE Advanced from 2020 paper 1. So here's the problem. Suppose A and B denote the distinct real roots of the quadratic polynomial x squared plus 20x minus 2020, and suppose CD denote the distinct complex roots of the quadratic polynomial x squared minus 20x plus 2020. Then find the value of this expression that we see here. The exam itself is multiple choice. I have not listed the multiple choice answers here because I just want to show a general way to solve it, but then I will relate it to one of the answers on the multiple choice. I can start with a few hints. The first thing is to recognize symmetry in the problem. We have two aspects of symmetry here. We have symmetry between the two polynomials. We see that they're pretty much the same except for we're switching signs here. And then we see that this expression that we should evaluate is also highly symmetric. So that's going to lead our thinking a lot here. So using the quadratic equation, for example, to solve this and find the roots and then multiply all this out that sounds like a nightmare and it's very messy and it's completely unnecessary. The symmetry here, and especially between these polynomials, will lead us to believe that there's going to be a lot of cancellation if we approach this the right way. And to do that, this should lead us naturally into the idea that we should use Vieta's formulas. And Vieta's formulas are equations relating the roots of a polynomial to the coefficients. And so the symmetry will lead us naturally into that, and we'll see that that's going to be a very easy way to solve this. And then we just multiply out the expression, factorize a different way, and then apply Vieta's formulas, and then we're done. So if you haven't solved this before, you can try and use those hints to see if that helps to solve it. Otherwise, I will go through it now. So I have the problem at the top again. I'll keep it there for each of these slides. I thought I had animation here, but I guess all these appeared at the same time. Sorry about that. So since we're going to be using Vieta's formulas, we can start by writing them out. And then I'm also going to write two more relationships based on them. So these first two here are, I'll talk about the bottom ones in a second. So these first two here are Vieta's formulas. And here we have the product of the roots is the constant term. And then this here with the sum of the roots is the negative in the middle. This is sometimes written as minus. It's very often written as negative a plus b is equal to the middle coefficient. So all I've done here is move the negative sign to the other side to get an expression for a plus b. But it's often written as negative a plus b is equal to, in this case, 20. So I just move the negative sign over for convenience. And we have the same thing for CD and C plus D, except the signs are, of course, reversed, which is what we see with the symmetry here. So the other thing I have shown here is I wanted expressions for a squared plus b squared and c squared plus d squared in terms of these Vieta's formulas. So I'm listing them here for convenience so I can refer back to them, but I don't have an expectation that you would see this at this point. So maybe if you were working the problem from scratch, you would write out these here in the beginning, Vieta's formulas. You'd start to go through the process of using some algebra simplification, and then you would see you had a need for these expressions here, a squared plus b squared, c plus squared plus d squared. And then since these are symmetric polynomials, which means that they look the same if I switch a and b, and they look the same if I switch c and d, that should lead you to believe that you can write them in terms of these Vieta formulas. And this has to do with like how symmetric polynomials work. And so if you think you can, if you look and see, oh, hey, it's a symmetric polynomial, maybe I could write this in terms of Vieta formula, then it's quite simple. And I worked through the details with one of them, and then it's easy to see the others the same. So if we start with just squaring a binomial, a plus b squared, then we have the very simple binomial expansion, which is equal to a squared plus b squared plus 2ab. And then if we just move the 2ab to the other side, we have an expression here for a squared plus b squared minus 2ab. And then we notice that each of these, a plus b and a times b, we have up here from the Vieta's formulas, a plus b and a times b. So now we have an expression for a squared plus b squared in terms of these Vieta formulas, which we have numbers for. So I'm just going to fill those numbers in now. So here, a squared plus b squared is a plus b, which is minus 20. So it's minus 20 squared, minus 2 times negative 20. And minus 20 squared is 400. And this is, of course, 40. And negative 2 times negative 20 becomes plus 40. We have a similar situation here, except this one becomes minus 40. Now, I've left them in this form. You could, if you want, add the 400 here and then subtract 40 here and come up with one number. However, I found it more convenient to leave it in this form because when I worked through the problem, I saw that we're going to be adding these, in which case these will cancel out, and it just makes the math that much simpler. But it's only a little extra work to add these together, subtract these, and then fix it later. So that's a matter of taste. So I found it convenient to leave it in this form. You could do as you see fit and find easiest. So all we're going to do is some simple algebra now. So this, I just copied down the expression here we're trying to evaluate. So the first thing I did is I just multiplied out all the parentheses. AC times A, AC times C, and so on. And then I'm going to regroup them in a way that's going to be more convenient. And I've color-coded the ones I'm going to group. And I'm grouping them by the squared terms. So we see that the purple ones both have an a squared. The green ones both have a c squared. The blue ones both have a d squared. And the red ones both have a b squared. So here I've kept the same color coding. And we can see that I've grouped them and factored out. So this plus that is a squared times c plus d. This plus that is b squared times c plus d. So I just regrouped and factored these colored terms. And we can see that this is quite convenient because I have a c plus d here, and I have an a plus b here and here. So that allows me to factor again, which is really nice. So if I factor out the c plus d, I get c plus d times a squared plus b squared. And then minus, of course. I put the minus outside because we have these two negative expressions, so I can just put the minus outside, a plus b times c squared plus d squared. And now I can use the formulas. I have numbers for these, so I can just put the numbers in, right? Because we know a c plus d, and we know a plus b from the earlier slide. So I just copied up the formula we had at the end there, and we just used the Vieta's form from the first page, right? So these are just the Vieta's formulas we used from the first page, and now we could just put in a plus b here and c plus b d there. And notice that a plus b is negative 20, but it's minus negative 20, so it becomes plus 20. So we have plus 20 in front of both expressions, which means that we can factor out the 20. So we can do one more round of factoring to make it. You don't have to, but I think it makes it a little easier to do another round of factoring. So then we get 20 times a squared plus b squared plus c squared plus d squared. And so it would be at this point you would see the need. I need to know what a squared plus b squared is, c squared plus d squared is. And so at this point you would go back and work out using squaring the binomial to figure out how to write a squared plus b squared in terms of Vieta's formulas. Because I had already done that, I wrote them on the first page for convenience. But maybe in the normal process, if you were working this out the first time, you would get to this point, and then you'd be like, okay, I need to figure out what a squared plus b squared is. Okay, I can do that simply in terms of Vieta's formulas by squaring a binomial. So we'll now use those extra formulas we built from Vieta. So here's the expression. I just copied it up again. And here are those extra formulas from the first page. A squared plus b squared is 400 plus 40, and c squared plus d squared is 400 minus 40. And so now we see, because we're just adding everything together, we see why it was convenient to not add these together, just to leave it plus 40 and minus 40, because they'll cancel each other. It just makes the math a little bit easier. Right, so when I put it all together, we see the red terms here. They just cancel out. In fact, I could just do this where they're just going to go bye-bye. Right? And some really simple canceling. They're just addition. And then, of course, we get 400 plus 400 is 800. We get 20 times 800 is 16,000, which is answer D on the exam. So that is the solution to this problem. I hope that was helpful.